Here I have drawn the glomerulus and the subsequent track of the nephron, and this is the afferent arterial and afferent arterial. And yeah, so I want to talk about a couple things with what's going on here. First, let's talk about how a concentration gradient is established in the medullas of the kidney. First, let's talk about how the GFR is regulated based off of pressures in our system. So we have this area right here that we call the macula densa cells. And they're going to participate in what we call tubular glomerular feedback. What happens here is these guys are constantly sampling the filtrant inside the tract here for sodium chloride concentrations. So really high sodium chloride concentrations means that, hey, we're getting way too much filtrant, we're filtering the blood at too quick of a rate, which is bad. So they're going to go through and they'll release one signal for that, and then they have a different signal for when they need to cause the filtrant to speed up, so meaning sodium chloride levels are low. Okay, so if there is too much sodium chloride in the system, they're going to go through and they're going to release something. They're going to release aldosterone. Adenosine. And they're going to act on, I guess I have that drawn right there, but really it's right here. Adenosine is going to act on the afferent arterial, and that's going to cause it to constrict. Constricting is going to decrease the flow rate, which is then, of course, going to cause our filtrant to come in slower. Just to show you what I mean by that, well, actually, let me do the other half of this first. So, and then the macula densas, they sample like, oh no, we don't have enough. What they'll do is they'll release something called nitric oxide, NO, and that'll come up there. And nitric oxide is a paracrine, so therefore it's a potent vasodilator, so let's go whoop, and we're going to get more flow through. This comes from one of the previous equations where we have, in the past we call it blood flow, but really it's any kind of flow that's in a non-closed system. Well, I guess it is blood flow because we're talking about this red line right here. And there's a couple variables like delta P, bunch of other stuff, but the important thing is that R to the fourth is on top of this right here. So as R to the fourth, or as our radius decreases, hence nitric oxide, our flow rate is going to decrease as well. And as we increase, our flow rate is going to increase. For me, it actually seemed kind of counterintuitive because we're Bernoulli's principle, but hey, that's just how it works. Awesome. I want to talk about ADH and aldosterone as well. So let's get rid of this. So starting with ADH. ADH is released by the hypothalamus, which is somewhere up in the brain, kind of in the midbrain. And it is a hormone that comes and acts on the right brain up here, which is really the hypothalamus, posterior pituitary gland, but who cares? ADH. And it comes and acts on primary cells or primary cells to open up these aquaporin channels. Aquaporin increases the permeability of water in the collecting tubule right here. This is also facilitated by these urine or urea transports, but we'll get to those here in a second. Aldosterone is produced by the adrenal cortex, but it's first stimulated by the release of renin, and then that converts to angiotensin, angiotensin 2. So we have the ROS system. I'll draw that out real quick, just so you can see it. So renin is released by some juxtaglomerular cells. So we have renin, and that's converted, and that converts angiotensinogen to angiotensin 1. And then we're going to add an ACE enzyme, and that's going to convert to angiotensin 2. Angiotensin 2 goes on to do a whole bunch of stuff, but for this part, we're going to talk about how it goes into the cortex, and it's going to cause the release of aldosterone. So aldosterone aldosterone has one effect. We like to say it increases water reabsorption, but really what it's doing, we also like to say it increases sodium reabsorption, but really what it's doing is it's increasing the activity of sodium potassium ATPases, meaning it's literally turning more on or creating more. So we get more ATPases throughout this area, and we get sodium coming out, we get potassium coming in to our cell, and that's going to cause more water to want to flow originally. So ADH and aldosterone really work together, or I guess you could say ADH and angiotensin 2, or ADH and renin. They all really work together. Section right here too. So this is called the loop of Henle. We have an descending and ascending loop. Specifically on the descending loop part, we have urea transporters. So for some context here, let's say we start at 300 milliosmol, and as we get down to here, especially in medullary cells, we're getting to 1200 milliosmol, which is crazy concentration. This is initially facilitated by these urea transports, UTA1 and UTA3, and they pump urea from the filter tract, not into the blood necessarily, but just into the interstitial space of the kidney. Now that gets all around here, because this is actually really tiny, right? And that creates a super hypertonic environment compared to the inside of our tract here, which makes water want to flow out since our descending loop is permeable to water. Well, that's good, because the whole point of medullary nephrons is to further concentrate our kidney, or further concentrate our filtrate. So we need to be able to create a hypertonic environment that water can just freely flow through. However, we do run into an issue with it because we do have blood, the water needs to go somewhere and it's going to go back into the blood. We have this issue where that would actually cause white or red blood cells to crenate, because that red blood cells like to be about 300 milliosmol. So once the urea gets transported out of here and it creates that hypotonic or hypertonic environment, that's good because we want water to flow out of the descending loop of Henle in order to conserve more water inside our system. But that's going to pose an issue for the red blood cells in the vasa recta, because that'll cause them to crenate, and we need our blood cells alive, not dead. So we have a urea transport on the vasa recta itself that helps pump urea into the red blood cells, so it's not a hypertonic environment, so it's an isotonic between these two, and then they get deconcentrated as they go on through. We might actually get some urea pumped back into our filtrant as well via the UTA2, in which case that'll travel and traverse until it gets repumped back out here. But that's very important for establishing concentration gradients.